Okay, so we are into compound motion. So we've talked about things falling, so vertical motion. We've talked about things being pushed or pulled, horizontally. Well, now, what if things happen in both, vertical and horizontal motion? So, like, I always think of it like a football player throwing a football, and it kind of makes this sort of trajectory. So it's going both this way and it's going both this way, and it kind of makes this, net force at this angle, which is a projectile motion. And some things that you need to consider at all times is that gravity is acting on it, and that the acceleration is independent of the object's motion. So whereas gravity is always going to be pulling down on this, right? No matter what. This horizontal motion, though, is happening because of the initial force. But after that person has let go of the ball, it has no force on it. So the only force it's acting on at that point is gravity. But that's independent of its motion. So those are some things that you need to consider. Projectile motion, vertical projectiles. So if you throw something up in the air, at first it's going to be going pretty fast, but then, gravity's pulling on it the whole time, so it's going to start to get slower and slower until finally at this point at the top, it's just going to sort of stop for a moment. And then it's going to accelerate downward. However, gravity is acting on it the entire time. Okay, just because it stops at the top doesn't mean that gravity is not still acting on it. So there's always a force. And then horizontal projectiles, the horizontal velocity remains the same no matter what. The only thing that's, causing it to stop is gravity. So this is showing kind of like an image of someone that's going to shoot an arrow versus somebody that's just going to drop an arrow. And the vertical motions occur in parallel, so the up and down is going to be the same. It's, going to take the same time for this arrow right here as it does for this arrow to hit the ground. Some people don't believe that, but if you YouTube some videos, it kind of show you how that works. Kind of cool. I showed you sort of the football. The only force that's acting is gravity, so it's constantly pulling down. And I like this image because see how this horizontal vector just stays the same through the entire process. It's uniform, where when we throw the football up, the force that we throw the ball up is more than gravity. That's why it goes up. But the more that it's in the air, gravity kind of takes over. And at this point right here, it's sort of like the most it can get, this top point. And then gravity just starts to pull it down until, eventually it would stop. All right, so the combination of those two motions make a parabola, which you've maybe heard that term in math before. It's just sort of like this curved sort of image. So, okay, that gets us into the 3 laws of motion. And you have to know these, okay? So figure out a way to memorize it. Now, you don't have to necessarily write them, but you need to be able to figure out, oh, this law goes with this number. Okay, so Isaac Newton was the one who came up with these 3 laws of motion. And this is saying concurrently developed calculus and a law of gravitation. So there's a lot of things that have, built on all of this. And the essential idea of all of these laws comes from the basic umbrella of forces. All right, so the first one, you guys have probably heard this. For every object that stays at rest, every object stays at rest or in its state of uniform straight line motion unless acted upon by an unbalanced force. I say it a little bit different. I say every object that's in motion stays in motion. Every object that's at rest stays at rest unless acted upon by an unbalanced force. Okay, so you probably heard that one before. That is Newton's first law. And it's also called the law of inertia, so you need to know that too. And so this is showing you a picture of like someone on a bus. And if the person on the bus is sitting sort of in the middle, or let's say they're standing, and the bus is originally at rest, and then the bus takes off pretty quickly, you're going to be kind of like thrown backwards because your body's going to want to stay in that same position that it was before. So it's thrown backwards because your body wants to stay at rest, okay? But because of the bus moving, you change positions now on the bus. And then this is showing you that if the bus keeps going in a straight line, your body kind of wants to stay in that. So if the bus turns pretty sharp, then you're going to be like thrown to one side or the other, because again, you're going to want to try to stay in that same position. Just like if you're in the car and you have a seatbelt on and someone slams on the brakes, you're going to go forward, right? Because your body's going to want to keep going. So every object stays at rest or stays in motion unless acted upon by an unbalanced force, which is also the law of inertia. All right, the second law, this should have like an equal sign right there. This is the one that's the hardest for people to memorize. It has the mathematical equation for one. So this is a new equation. And basically it's saying that force causes acceleration and it's proportional to the mass. So let's take a look at this equation for a minute because it really does help to see the equation, in my opinion. And I actually like to rearrange this equation. So I like to solve it for acceleration. And see how many variables there are? There's 3. So that means that you could put it into a triangle if you wanted to. You could say force is equal to mass times acceleration. So if I'm solving for acceleration, then that means I have net force divided by mass. Okay, so when I say net force, I mean like you could be pushing one way and pulling another. Remember like the tugboats? But they have to be, you have to get the sum of it, okay? So let's just say, for example, and I do think that there is a picture that shows this. Yeah, I love this one. So say, for example, that you're riding on a bicycle, okay? And I'm going to go back to this equation now. Just kind of get the image of yourself riding on a bicycle. Okay. If you put a lot, let's say you're on there, you know your mass, you know about how much you weigh, even though weight and mass is different. We'll get to that in a minute. But you know your mass, you get on a bicycle, you're going to have to apply a certain amount of force in order for that bicycle to move, correct? Otherwise, you're not going to move. So if you apply, let's say, I don't know, some force, and you move, and then you apply twice that force, do you think that you're going to speed up or slow down? You haven't added any weight at all. It's still you. So if you add more force, you're going to accelerate and go faster, correct? Yeah. Now let's say that you have the same amount of force. So let's say this was what I did before. I'll just make like a line. Instead of numbers or anything, I'm going to say, okay, you have this much force and you have this much mass. You're going to accelerate, right? Because you're applying more force. And if I do this and I didn't change my mass at all, I'm going to go faster, right? Okay. Now, what if I take this much force that I was doing originally and I add another person on the bike with me? Now, am I going to accelerate or decelerate? So I'm applying not very much force, and now somebody's jumped on the bicycle with me. Well, that's going to make me, not go as fast. So I'm going to decelerate. And then if I, you could just keep going and going and going. So what this is saying is that acceleration is proportional. That's kind of a fancy little symbol for proportional to force. The more force that you apply, the more acceleration that you have. And it's going to say that, I think this is actually in here. Oh, no. And it's also saying that, if you don't, or if you put more mass, then that's inversely proportional. Okay? So, kind of like this. Acceleration is proportional to 1 over mass. Okay, so inversely meaning like it's, on the denominator. Okay. And that's what it's saying right here. More force, more acceleration. More mass, less acceleration. All right, so Newton's second law has some math a little bit to it, meaning that there's some examples, okay? So let me go to our notes here so that we can kind of do one of those examples. So this is example 2.8 in your book, and it says a 60 kilogram bicycle and rider, so both, accelerate at 0.5 meters per second squared. How much extra force was applied? So it's wanting to know the force. Okay, so kilograms is a unit for what? Mass. Meters per second squared is a unit for what? Acceleration. So our equation here is force is equal to mass times acceleration. So do I need to rearrange anything? No. So mass is equal to 60 kilograms. Acceleration is equal to 0.5 meters per second squared. You multiply those out. You get 30 kilograms times meter per second squared. Okay, now this right here, because this is Newton's second law, this is shortened to what's called a Newton. Okay, so a kilogram times meter per second squared is the same thing as a Newton. All right, and so let's do example 2.9 really quick. This is saying, what is the acceleration of a 20 kilogram cart that has a net force of 40 newtons? Okay, so 20 kilograms is mass, 40 newtons is force, and it wanted us to find acceleration. So do we need to rearrange the equation now? Yes, we need to arrange it like how I had it on the previous slide. So now we can take our force, which is 40 newtons, divided by our mass, which is 20 kilograms. And this is why it's a really good idea to know what a Newton is. So a Newton is a kilogram times meter per second squared, divided by 20 kilograms. So you're going to take, and your kilograms are going to cancel. 40 divided by 20 is the same thing as 2. And what is left after you cancel that kilogram? It's going to be meters per second squared. Okay, are we good on significant figures? Yes, those zeros didn't have decimals after them, so just one significant figure for 20 and 40, so we're good to go. Okay, I think I need to stop the video, and then we'll get on to weight and mass.